Okay, so now that we have seen how to implement address decoding and thereby communicate with external peripherals, we are going to look at an extension of this or a generalization to the idea of a bus interface. So, as we move from isolated components to complete systems, we face a number of integration challenges, right? There are problems such as signal standardization, which on the one hand could be electrical signals in terms of what kind of voltages and so on to use, but the other could be something like what are the control signals. I mean, in other words, how many bits should the address bus be, how wide should the data bus be, should I be giving a read enable, write enable, chip select, what are the different kinds of signals that are required, right? So, this standardization of these signals across the different CPUs as well as peripherals that we are trying to communicate with is important. Coordinating the timing. Maybe peripherals have been designed to work at a certain speed, let's say 50 megahertz, but the CPU is trying to work at 200 megahertz, and then it needs to know that it has to basically wait before it gets the data back from a peripheral. Or it could be the other way around, maybe the peripheral is running faster than the CPU, right? There are certain resources that actually get shared across multiple parts of the system, in particular the wires that are actually used to communicate the different parts. When we look at it in an abstract logical way, it turns out that those are actually sort of common resources shared across multiple different peripherals. And of course, given a scenario like this, there is also the possibility that something goes wrong. What if a peripheral does not respond, or if some wire is not connected properly? How should the entire system respond, and what will happen as a result? So, what comes out once you sort of think this through and what has evolved from experience is this notion of a so-called bus-based architecture, right? And this picture over here is a generic depiction of what a bus-based architecture looks like, right? There is this big block out here, right, called the system bus, right? And the program memory, the data memory and various peripherals are all connected to this bus. And from this picture at least, it looks as though the CPU is just one tiny thing sitting on the corner communicating with the bus. And in fact, in terms of the sheer space occupied, in some sense this is true, except that of course the CPU in modern practical systems is not as small as what it looks over here, and the bus is not really a very big physical device. The reason why it looks big is because there are many wires that need to go across over here, plus there are of course the multiplexers, decoders, and so on that are associated with the bus activity, right? So, this notion of a bus is a very powerful abstraction that allows us to sort of build systems by saying I have a common system bus, and as long as the different peripherals and the CPU know how to talk to that bus, they can then in turn talk to each other, right? So, it is a shared communication pathway. There are many common examples of bus types, right? You could have an address bus which is basically unidirectional, it is always coming out of the CPU. Data buses are bidirectional, meaning that you could either be sending data from the CPU or trying to read data back. And you can have the control bus, which is typically things like the read write enables, or there could also be maybe an interrupt signal coming back from a peripheral or some kind of acknowledgement coming back from peripherals and so on, right? So, all of these are typical signals that need to go as part of the bus. And obviously by looking at it, you can see that it's quite possible for somebody to come up with one set of signals where we decide that maybe rather than having a separate read and write enable, I'll just use a single enable signal and say that if it's 0 it's read, if it's 1 it's write. Maybe I have some other thing for a chip select. Maybe I can have a clock which runs at a different speed than what the CPU is using. Do I need to use an active high or active low reset? Do I even need a reset at all? Should it be synchronous? Do I need extra signals for ready wait? All of these are different options, and clearly if we choose different options over here, it's quite possible to make it such that my CPU and my peripheral choose a different set of options and therefore cannot talk to each other, which is why of course we want to standardize the type of bus, and the whole notion of a standardized bus architecture becomes useful. Right? Now we also have, as part of this thing, what we can do is bring in this notion of something called handshaking. Handshaking basically says that I'm going to take this idea of reading and writing to the next level, by saying that rather than just saying the CPU puts out an address and waits for data, the CPU puts out an address, or rather puts out an address, and in the next clock cycle it assumes that the data is already present. It can be made to actually wait, meaning that if the data is not yet present, the bus can tell the CPU, wait. It just asserts a signal over there that says, wait, the data is not yet ready, and the CPU either needs to just wait, or in some cases it might be that the CPU can go ahead and do something else and will get alerted when the data is actually present and can be read back. Right? The point is, this is effectively a form of handshaking. It allows two different peripherals that run at different speeds to be able to communicate in both directions. So there is a signal that requests for a transfer, typically coming from the CPU or a bus master as it is called, and there is an acknowledgement of the request, and if necessary some kind of permission to actually use the resource, either the bus or whatever else is being requested for. Right? You can have variations such as either synchronous or asynchronous bus protocols. Synchronous typically means that everything is running with the same clock. Asynchronous could be when you have something which needs to issue a signal but is communicating with a device which is happening at a very different speed, and therefore rather than waiting over there for the data, it sort of waits for some kind of a signal to come back from the bus indicating that the data is ready. Handshaking essentially is useful in such scenarios, right? What we do is that the CPU sort of requests data, the device that is trying to give back the data acknowledges the request but may not give back the data, and finally it gives back the data when it is ready, and the CPU can then accept the data and do something with it, right? This also makes it easy to insert the idea of wait states, meaning that if I have a peripheral that is slow, the peripheral could acknowledge that it received the request. That could happen immediately. In fact, the peripheral may not even respond. It may just be the bus logic that tells the CPU, okay, I got the request, now I'll go get the data from the peripheral and I'll wake you up again when the data has come, right? So you could either do that, or you could just tell the CPU, you need to wait, I will let you know when the data is ready. And you can basically make the bus, or rather make the CPU wait until the data has come back, and by doing that you can accommodate slow peripherals. Right? There are many different ways in which this gets implemented. We are not actually going to look at how it's implemented in practice. At this point I just want to talk about it as a concept that could be used. Now, as I have mentioned over here, right, the standardizing the signals, the kind of signals and the nature of signals is the important part of what defines the bus. But there can also be advanced bus protocols. In particular, you might have a scenario where you have different peripheral speeds, and this is quite common. Even in a microcontroller, of course, you have to deal with memory. You might be outputting something to video, which generally tends to be high speed because you have a lot of data to be sent out onto the screen and refreshed many times per second. Similarly, you might have data that's coming in on Ethernet, which is a fairly fast protocol. It can go into the hundreds of megabits or even possibly gigabits per second. On the other hand, there are plenty of low speed peripherals. Examples would be the keyboard and mouse, which are human interaction and therefore work more on the milliseconds to tens or hundreds of milliseconds time scales, or even something like printers, right? They tend to be fairly low speed compared to the other kinds of devices that you have. You could also think of something like a UART, right, which is at the end of the day only in the hundreds of kilobits per second compared to Ethernet, which is hundreds of megabits per second. So we clearly have like several orders of magnitude differences in speed. How do we handle such things? So the ability to handle wait states efficiently, flexibility in doing this becomes very important. There is also the notion of something called a burst transfer, which says that, let's say I want to copy several words of data from one location in memory, either into another location in memory itself or from one location in memory to some peripheral. One way of doing it would be that the CPU actually individually reads data from each location and then writes it into the destination and runs this in a loop, and that's of course the commonest and the simplest way of writing the code. But then the CPU doesn't really need to be involved in this, right? All that it's doing is taking data from point A and moving it to point B. It should be fairly easy for a simple piece of logic to just do this kind of a transfer. There are of course certain kinds of peripherals in most microcontroller systems that do precisely this. This is exactly what DMA, for example, handles, right? Direct memory access. Now, what happens in such a cases, it can also simplify things further and say that rather than taking individual elements one by one, reading them from one place and writing them somewhere else, let me just issue what's called a burst transfer, right? And the bus itself will take care of generating the successive read and write addresses on its own without having any other logic intervening. They do this because this is a fairly common kind of operation, right? There are many scenarios where you want to copy chunks of data from one set of addresses to another set of addresses. So why not make some extra hardware support for it? Now, with all of that in mind, this is a typical picture that comes about. In fact, this picture is taken directly from the data sheet for the AMBA bus, the Advanced Microprocessor Bus Architecture, right, which is defined by ARM. And as you can see, there is the ARM processor, which is the high performance system sitting over here. And the way they define it is the AMBA architecture has like multiple different ways of handling things. You could of course have the CPU talking to a high performance memory, right, which has a very high bandwidth. You could have high bandwidth on chip RAM, which also the CPU needs to be able to access. And then finally there is this device out here which is called the DMA, or direct memory access bus master, right? And the main point of a bus master is, a bus master in this context over here is something that can initiate a transfer. Usually the CPU is the one that initiates transfers. It says, okay, I want data from this memory or from somewhere else or from a peripheral, give me the data. But in this case, the CPU, we don't want the CPU to be permanently occupied in moving data around from one place to another. Instead, the CPU can just tell the DMA unit, can you transfer data from, let's say, the external memory to the UART? And then the DMA would take over and wait for the bus to become free. Whenever the CPU is performing computations and not using the bus, the DMA would say, okay, let me take data from here and send it to here, right? So having an additional bus master relieves some load from the CPU. But as you can see, there is also this bridge that is sitting over here and saying, okay, everything on the left is a high performance peripheral, everything on the right is slow speed. Rather than trying to communicate directly between them, let me put in a bridge whose job is to make sure that if something slow is coming in over here, it gets converted to the clock speed running on the left hand side. And clearly anything communicating here is going to have to wait if it needs to communicate with the right. So let me take care of the handshaking signals also in this bridge part out here. Okay. So this is a very generic form of bus architecture. It is one of the most common buses for microcontroller based systems nowadays, primarily because ARM is the most common form of microcontrollers that is available. And RISC-V has also, most RISC-V systems also have some kind of support for the AMBA protocol, or to be more accurate, the more updated version, which is the AXI, or AMBA Extensible Interface, the protocol, Advanced Extensible Interface Protocol, which is also from ARM. As I said, there can be a number of complex bus transactions that are possible in some kind of a modern bus like this. You can have things like non-sequential transactions where the address basically could jump to different values. You could have something where it essentially says it is going to be busy and the bus is not used over here, right? I don't want to go through this entire picture in detail. The point is that this is directly from the AMBA bus architecture document, right, and indicates various different kinds of transactions that can be performed. The point of this is not to sort of go through and understand what are the different architectures or different kinds of transactions that we have. It's more to sort of indicate that yes, buses can be complex, they have a number of different signals over here that are relevant to them, right, and they can also perform many different kinds of transactions, as you can see over here, right. We are not going to get into the details of these because it's not our purpose to look into or to understand exactly how the AMBA or AXI buses work at this level. Now, so far we have looked completely at the hardware point of view. What would the software look like, right? And this is something that we have already seen to some extent in the embedded C programming. Ultimately, what we would have is some kind of a set of hash defines perhaps that are present in your C code, which basically indicate the base address as well as the actual addresses of data, the direction register, the interrupt enable register and so on, right, which would be defined as some kind of pointers to a base plus an offset, right. And by essentially defining it as a pointer, what it means is that the CPU, when the compiler actually works, it will actually generate an instruction which will be a load or a store instruction. So if I try writing something to a GPIO direction register, it would take this pointer and try to perform a store operation to that, right. If I try to read some value back, for example, if I want to take out the GPIO data, it would basically read from this location, and that would be a load operation that comes in over here, right. So in other words, by defining the base and offset addresses that we have over here, it is possible for us to use a language like C directly in order to communicate with the peripheral. And what we have seen so far in the rest of this series of lectures is what does the hardware side of things actually look like. So from a software interface point of view, this is the most basic form, directly accessing registers. In most practical scenarios, you don't do this. You actually write some kind of a device driver, which is a set of functions that wraps this into easier to use programming interfaces, right. And then once you have device drivers, you put multiple device drivers together, you get an operating system. And then once you have an operating system, you actually have a full-blown application programming interface that can be used in order to develop more complex applications. So to summarize, the bus-based architecture is what enables modular system design, or rather is one of the approaches that enables modular system design. Memory mapped I/O provides us with a nice unified programming model, right, which is nicely exploited by the bus-based architecture. Having standardized interfaces or a standardized architecture for the bus simplifies component integration. There are multiple buses in existence. Intel uses their own bus architectures for the peripherals that are tightly integrated with their CPUs. There is something called the Wishbone bus architecture that was defined as an open standard. Nowadays, as I said, AMBA and the AXI bus protocols are probably the most common standardized ones that exist. They happen to be open protocols, which is also good, which means that anybody can read up the documentation and implement peripherals that are compatible with those protocols. The actual integration into a large system requires careful coordination of the various kinds of signals used as well as the timing between the signals. And if we design the hardware keeping all of these things in mind, it enables us to write clean and efficient software as well.